Okay, so we were discussing about the phonon scattering events, and I intend to finish this discussion today and get over to some high field transport phenomena. And I think I'm realizing that if every one of these topics is an infinite sink, so you can spend all your time getting deeper and deeper into it. But I'm going to cut it off. So today will be the last day of Boltzmann transport equation and such. Starting Wednesday, we get into some other things, the next topic. Okay, so today is the last day. And as I have mentioned a couple of times, I've given you handouts as well as there are quite a few books and references, specifically the books I've referred to in the class website. I have a lot more detail about Boltzmann transport than what we are covering in the class. My intention in the class is to give you the main ideas, and I think hope you can take it from there. And okay, but since the reason I'm going into the phonon scattering aspect of it in some detail is because I have mentioned earlier we were going to do correlated transport, and the best example of that being superconductivity. And today we are going to look at the particular interaction that leads to superconductivity, but the normal BCS sort of superconductivity. But we're not going to discuss too much about superconductivity today. Okay, so we're going to just set up how does the electron-phonon interaction term look, and I will point out where we will pick it up from when we discuss superconductivity. Okay, so in our discussion of electron-phonon interactions, we wrote down that the electron will experience a certain perturbation potential compared to the perfect crystal situation where there is no perturbation. So the presence of a phonon will lead to a certain potential for the electron, and that potential always has a wave-like form, right? And the wave we were writing as Qs dot r minus omega of Qst, right? And here Qs is the wave vector of the phonon, and omega is the frequency of the phonon, and they are tied together by the phonon dispersion. So they're related. And then there's some stuff sitting out here in the front. Okay? Some stuff sitting out in the front. And typically, we are going to essentially be able to write it in this form. So there will be a U of Qs, which will be the amplitude of the phonon vibration, the amplitude. And then there will be some coefficient out here, which we can call right now as W of Qs. We just call that for argument's sake. And there's a coefficient, then there is an amplitude, and then there is the phase for the wave. Right? So and we'll see that every phonon scattering process we can write it in this way, pretty much. And then once you have that, the phonon scattering rates, etc., are standard after that, because you're going to take this just as the bigger picture of that is the total system Hamiltonian has electrons and phonons now. So it's they're both together. So if I were to write the total system Hamiltonian, I should be writing electron momentum operator square by twice the mass of electrons plus the potential that the electrons see, and that is the periodic potential of the crystal. I'm just writing it formally, the whole thing now. Okay? So this is the periodic perturbation of the crystal. So this is all the pure electron Hamiltonian. That will give you electron energies. Plus the phonon Hamiltonian will be terms like, again, this is, I'm writing it somewhat qualitatively now, but so it will be something of the order of omega squared, omega, this Qs squared times the length, or r squared. So this is half kx squared, sort of. That's the potential energy of a mass spring system. half kx square, and m omega square is the spring constant for that, right? And these are the masses of atoms and actually related to the mass density, etc. So that's the half. Okay, so that's the energy. We can write it potential plus kinetic. This is similarly the kinetic energy of the electron plus the potential energy of the electron. Similarly, you can write the potential plus kinetic. So plus kinetic of the atoms, the mechanical motion. This is the electronic, this is the mechanical energy, and plus the interaction between the two. So this is electrons, this is phonons, right? And then the interaction term is this. This is what we are after, right? So this is the interaction term, potential that the electron sees because of phonons, and vice versa, the phonon sees because of electrons too. And this is essentially the electron phonon term. That's the total Hamiltonian, so this is basically a big H. And the Schrodinger equation tells you that d psi by dt, where psi, I'm kind of outlining the full-blown picture which treats electrons and phonons at equal footing. And therefore, the psi should really be a product of psi of electrons times some psi of phonons now, right? So it's both systems. Right? Just like we had written 2 electrons, 1 and 2, so product. Similarly, it will be 2. And later on, we'll see that to understand aspects of superconductivity, etc., we are going to deal with the full-blown wave function. Right now, what we are doing is we are saying that the perturbation term is it's a small change to the electron Hamiltonian, and we are saying that what this has done is it has created your phonon band structure, h bar omega of qs, right? So it has created acoustic and optical branches. What this has done is it has created your electron band structure, right? E versus K. It has created conduction bands, valence bands, and all that stuff. And this term is letting you the two interact, exchange by exchange of particles between this and this. And the rate of exchange is what we are after. The rate of exchange is again we are saying that we are working in this Fermi golden rule approximation. K prime whole squared, and then you have your energy conserving plus minus h bar omega of qs, right? So that's what we are after. And so the picture is, if I have an electron at this energy, and it can now go to either this or that, where it can gain some h bar omega, lose an h bar omega, and correspondingly here you'll have loss or gain. So to balance that, and that transition rate is what we are trying to calculate here. Right? Okay, so the first shot we are going to take is actually the phonon part of it will be kind of same everywhere. It will cancel out, and later on we'll treat them as quasi-particles where electron phonons are coupled very strongly, and that's where we get the Cooper pairs. And so right now we are going to treat them as independent approximation. Okay, so what we did in the last class was spend some time trying to understand. Again, this is the generic form of the of your perturbation potential because of electron-phonon interaction, the generic form, right? And what happens as you go from acoustic phonons to optical phonons to from a longitudinal, piezoelectric, all that sort of polar optical, this thing just changes from one to another. So everything else, I mean, it looks similar, but this matrix element kind of changes. Actually, I shouldn't call it matrix element. This is really dependent on R and also QS. So QS is just one mode of the, as you can see. So it is just every mode has its own value of W, own strength. That's really the physical meaning, and its own U, the amplitude. Okay, so we spent some time trying to understand why. So let's look at the result we ended up in the very towards the very end of last class. We said that we are looking at longitudinal acoustic phonons, right? LA phonons. And we realized after some discussions why the energy change would be the deformation potential, which is deformation potential essentially is the change in the eigenvalues of the band structure, the change, how much will the conduction band shift if I strain the semiconductor, right? So that's the deformation potential. This is in units of electron volts because the change, for example, of the conduction band. Okay, so let me just, that part is, okay, so that's your whole picture that we're going to look at. Right? So the change in the conduction band edge is the conduction band deformation potential times the strain, R comma T. And strain is dimensionless. So deformation potential is in units of energy. And I mentioned last time it's about 10 electron volts or so in most semiconductors. So just as what does 10 electron volt here physically mean? It means that if your strain is 1%, right? 1% is 0.01. So it will change the conduction band by 10 eV times 0.01. So about 0.1 eV. Actually, 0.1 eV is very large already. So something like that. Okay? So these changes are not terribly large compared to the gaps. Obviously, if you have very small band gap semiconductors, then this becomes different. But okay, so we saw that we wrote as the divergence, and divergence was the strain, as we realized, right? And from here, we got that because your U for any mode beta looks like U beta. So let's put a little unit vector showing the direction in which the vibration is occurring times E minus omega QST, right? So that was our they put a little n hat showing what direction is the oscillation of the atom, right, for the vibration. And we saw that when you take this dot product, what you get is the deformation potential, then the dot product, the divergence will pull out the IQ to the front, and you get I and QS dot product with N, when N is the unit vector in which the polarization of the vibration. And then you get the rest here, U beta, E. Okay, so, and from here already we had discussed why this will immediately lead to, for a transverse acoustic, QS and N are perpendicular, so this becomes 0. So the transverse acoustic, at least for points of high symmetry, does not scatter electrons, whereas the longitudinal acoustic does, right? Because QS is the direction in which the wave is propagating, and U of this N hat is the direction. So for transverse acoustic, N hat is going like that, whereas QS is going like that. But for longitudinal acoustic, N hat is going like that, right? So it's vibrating along the direction of the QS. And in that case, for longitudinal acoustic, this dot product just gives you a 1 because they are collinear. So you just get a QS here, right? So that's. And then that's something we derived in the last class. And you see right now that this is really in the form that I was mentioning, that it is some coefficient. And that coefficient here happens to be I times deformation potential times the wave vector of the phonon, right? Times the amplitude of the phonon vibration times the phase vector. So that's like that. And what we want to do now is look at, once you have this formulation, then you can kind of plug it in there and go forward and calculate all your scattering rates, right? So let's just look at how does this term look for some other phonon scattering mechanisms. So that's something we can discuss a little bit right now. Okay? So the second one we're going to discuss is what's called the optical deformation potential. Okay? So optical deformation potential. So just to summarize then, maybe we can create a little table here of our W of QS, which is what is this coefficient W of R comma Q. As you can see, actually the R won't appear there, so I'm just writing it for rather phonon mechanism, and then all right. So longitudinal acoustic. I'm going to write deformation potential because this is really remember the body in theory of deformation potential. For that particular process, our coefficient happens to be I dc times QS. Right? QS is the wave vector. What are the units for this coefficient? So, and if you, what will the units be? You can help me. Deformation potential is energy, right? And Q is wave vector, right? So it's 1 over length. So it's energy over length, energy over length, and so all of them should be the same. When I look at it for other mechanisms, it should also be energy over length, right? So we are going to look at optical deformation potential, and this particular one is saying. So remember the reason why we ended up with a divergence here, or to get the strain, is because all the nearest neighbor atoms, right? They were oscillating. The phonon, they were oscillating in phase, right? And then nothing, and then they were oscillating in phase. And we realized that if you don't have a divergence, meaning if both, all of them, so it can lead to a complete translation if all of them oscillated by the same amount, right? But if you go to optical phonons, it's not the same, right? Optical phonons, the next nearest neighbors are oscillating opposite in phase, right? So, right? In an optical phonon, they're going out of phase. So we can look at a few pictures for it. Here's an example. Optical phonon. As the wave goes through, the red and the gray ones are oscillating out of phase. So you don't need a divergence here to get strain, right? The displacement itself is going to give you strain. You see that, right? You don't need any divergence here because they're out of phase. And therefore, this is actually very straightforward. So for optical deformation potential, W of R comma T is going to be just the strain is due to the displacement directly, actually the difference, the displacement directly. And then you have an optical deformation potential. That's it. Nothing more fancy than that. So that will be like U QS e to the power I. Okay, so it's just one. And so for LO, longitudinal optical, and again deformation potential mechanism, this will be just D naught. That's it. Oh, OP. Yeah. And the optical phonon has units of energy over length. And typically this is of the order of, I forget, 10 to the power 8 eV per centimeter, or about, of the order of electron volt per angstrom. So all these things, so all energy scales in the semiconductor are of the orders of electron volts, and the length scales are all lattice constants of order of angstroms. So that's the natural length scale, and indeed that's what appears of the order of that. Okay, so that's that. For LO, because it's optical phonon, you don't need a divergence of the strain anymore to get the strain. It directly causes a strain. Right? Okay. Yeah, Sam?
How do you have a W with units different from energy? Does that not mess up the units in
I see. Say that again. The units are different from energy.
So is that the units of W are energy per?
No. Okay. W is always in energy, right? This deformation potential is energy per length. And then you have the amplitude, which is the length here. So it's back to energy again. Yeah. So, yeah. Right. So the optical deformation potential scattering, if you remember this omega qs and qs here, the major difference between the two here is here omega qs is the acoustic phonon. Right? So if you look at very small, near the middle of the billion zone, near q is equal to 0, this is linear with the sound velocity. So this is of the order of sound velocity times qs. Right? Whereas here, this is optical phonon, so omega qs is basically a constant, which is the optical phonon energy roughly. It's this one. Okay. So what does that mean? It means that omega of qs here for acoustic modes can go to 0. This cannot. This is so this is essentially massless, if you might, and later on we'll see what that means. Okay, so that's optical deformation potential. Now we'll look at two more. One is, and so these are essentially mechanisms that occur in all semiconductors. So you see the LA deformation potential acoustic phonon and deformation potential optical phonon occur in all semiconductors. But the next two we are going to look at occur only in polar semiconductors. Polar semiconductors are semiconductors which have two different atoms in the unit cell, gallium and arsenic, gallium and nitrogen, or things like that. Boron and nitrogen, boron nitride, for example. Whereas if both are silicon or germanium or carbon, then these occur for all. But the next two are related to charge on the two atoms and the electronegativity difference between the two. And so let's look at those two. So the first one we're going to look at is piezoelectric scattering. Piezoelectric phonon scattering, and this is a part of the longitudinal acoustic mode. So LA mode can scatter by two mechanisms. One is this deformation potential, which is due to strain, etc. And the second is if strain gets coupled also to charge in the semiconductor, which is happens in polar semiconductors, it leads to this additional mechanism, which is the piezoelectric. So both of them operate. So for piezoelectric scattering, if you understand the argument, you'll see that this is exactly similar to very similar to what we'll look as the in compound semiconductors. The most at room temperature, the strongest scattering mechanism is also related to charge, and it's related to optical, not acoustic. And but both the mechanisms look similar when you try to understand, where was the origin of charge. Okay, so the phonon now has caused vibrations, and now you can imagine that if these atoms were slightly positive and slightly negative and slightly positive and slightly negative and so on, right? And you have this wave of strain and of compressive and tensile strain going through, then you have now you have microscopically you can imagine you have dipoles that are you have dipoles that are going like that, right? Positive and negative dipoles going like that, and if you go down very microscopic picture, or rather, if you look at electromagnetic theory, we know that the displacement field is equal to epsilon naught permittivity of vacuum times electric field plus the polarization of any material. Inside any material medium, your displacement vector is equal to electric field times permittivity plus the polarization vector, right? And if you are in vacuum, there is nothing to polarize, so this is 0 in vacuum, right? No atoms to polarize, so this is 0. But inside any material, this will be non-zero because there are atoms and electron clouds, and you can polarize things now, right? Now, if you have any material now, the polarization, you're polarizing atoms, and so essentially what are we doing? So if I have electron cloud around the atom and I put an external field, the electron cloud will stretch out in response, right, and try to screen it, that part of it, the direct electron cloud part of it is called electric susceptibility. Right? This is sum over all electron clouds and all that times epsilon naught times electric field. So that's called dielectric susceptibility. It's just basically the response of the electron cloud, which is a little more, they can react to the electric field much faster because electrons are way lighter than the nuclei. Nuclei are very much heavier, right? About 2,000 times or something like that. Plus, any of these things because of these dipoles that form inside. If you have piezoelectric polarization, spontaneous polarization, then you will have some dipoles per unit volume. Okay? And the definition of polarization vector is the number of dipoles per unit volume. That's the definition of polarization. So let's write it small I, small p, over unit volume. Let's say the volume of a unit cell or something like that. Actually, let me not write it like that. Okay? Let's just write it as any extra polarization, and let's call it piezo for now. Okay? Not all materials are piezoelectric, but all materials like silicon or germanium will still have atoms, and they'll still have this. Right? But not all of them will have this. Right? This will be there for polar crystals. Okay? And the amount of the thing here is actually, you can write it as the piezo. So the way it's written is basically how much piezo polarization do you have? It's basically, again, a coefficient times the strain. Because if you remember, the coefficient times the strain, R comma T. It's very, very much like how much does the band structure change. You have a deformation potential, linear coefficient. Similarly, the linear coefficient of piezoelectric polarization is a coefficient. Well, it's a number, right? With some units times the strain. If you don't have strain, you don't have piezoelectric polarization. So does it make sense? So this is kind of the way you kind of model this in a simple way, and it behaves very nicely. Meaning, experimentally, you have the most polarization coefficients that obviously are linear to a certain amount of strain, and then they get nonlinear if you go very high in strain. But they're linear for low strains. Okay? So does it make sense? I mean, this is essentially just a coefficient again, and from here you can see the units will be basically Coulomb per centimeter square because all the others are charged per unit area. So this similarly, this thing, because strain is dimensionless, this will also be Coulomb per centimeter square. And strain we already have found is divergence of U, right? Where U is the vibration amplitude, right? So now our goal here is to find find the scattering potential, W. That's what we want to find. And the way we do that is we realize that well, I can, if I know my electric field that an electron can experience, I can find the potential, because potential is an integral of electric field. Electric potential is an integral of electric field, so that's what I need to find. And immediately you see here the argument that the displacement field, we are assuming, so the electron charge density that is moving through the crystal is low enough that your divergence of D is actually 0. Divergence of D is the free charge, right? Free charge per unit. Divergence of D from Maxwell equation is the free charge, not the bound charges, but the free charges. And if I look at divergence of D in this way, and you assume that D is some D naught, some constant times some unit vector. We know what direction the electric fields are. That's not a problem. Times a cosine of some wave vector dot r. Let's look at it one dimension. It's easier to do it. Dx comma t is no vectors here. You just get a cosine of some wave vector x minus omega t. That will be the wave of the displacement vector. And if you take divergence in one dimension, you just take d by dx. Right? And what you get is, the q comes out, q d naught, and then there's a sine of this whole thing. And what we're saying is in the absence of free charges, this thing is actually 0, which means that q is not 0 because you have a wave. So therefore this can take, I can take a point of time when this is not 0. That means the displacement has to be 0. D naught has to be 0. As a result of that, this has to be 0. That's what it's saying. So if you don't have free charge, then the displacement vector is 0. And you can see that it's a bit of a strange argument because we are looking at transport of free charge. Right? So there is free charge which is moving. But the argument here is if you compare it to all the other charges in the system, which are atomic charges, this is way, way smaller. Right? I mean, we are looking at, compared to 10 to the power 23 atoms per centimeter square and such, this electron density is way smaller. You can always go back and change this. And what will happen is it will change what you call as the dielectric constant. It's a little dependent on carrier density, but that change is very small. Is what I'm saying. So this is a great approximation. It might seem very weird initially, but it's a great approximation. After all this is said and done, what I'm trying to say is this left-hand side is 0. So that's what happens. See, I'm trying very hard to get the potential, and from here right away you see that. When you combine these two, you get epsilon 0 times 1 plus electric susceptibility times electric field plus the piezo coefficient times the divergence of u must be equal to 0. And what is 1 plus electric susceptibility? That's the dielectric constant of a material, right? That's the relative dielectric constant, right? So 1 is the dielectric constant of vacuum, and plus whatever, if you have atoms in a crystal, then that's chi e, right? What is the value for most semiconductors? I mean, the sum is about 10, so this is about 9 or so for most semiconductors, right? So chi e, the electric susceptibility, is just a number. So this combined together is called your semiconductor dielectric constant, and I'll for now just say it's a low frequency dielectric constant, epsilon semiconductor at low frequencies electric field. That should be equal to minus, I'm just moving the equations around, piezo and divergence of u. Let's just write it as du by dx for one dimension argument. I think you can easily generalize it to multiple dimensions. So electric field x comma t. And from here you get electric field is equal to minus the piezoelectric charge over the dielectric constant, low frequency dielectric constant, times du by dx. That's the electric field. So when the phonon wave goes through, it goes through the crystal and the atoms are slightly ionic, okay, this is the electric field it creates. That's the meaning of it in its wake. I mean, actually as it moves through, because of the strain and all that, the strain multiplies by that and creates this electric field. For silicon, E piezo is 0. So there's no such thing. Right? Does that make sense? Okay, yeah. For gallium nitride, it's actually very large. It's extremely piezoelectric material, so it's very large. And if you have crystals like lithium niobate and barium titanate, these are very, very high, even like 10 times higher than gallium nitride. So for example, gallium arsenide is about 10 times lower than gallium nitride, and they have a whole hierarchy of more and more polar crystals. Okay, so if I have the electric field, then the potential x comma t is minus electric field an integral of dx, right? Does that make sense? So that's the potential. Potential is force times distance integral. So you integrate it, and you see right away that d by dx basically just goes away here, and so you get w of xt is electron charge times piezo coefficient over epsilon s of 0 times the strain, directly the strain. The integral takes away this d by dx again. So you're just left with strain, which will look like, I'm just reinstating all my three-dimensional glory right now. I'm just, well, okay, yeah, let's just, you can go through this and make sure that this is correct. So, E dot dr. So there'll be a dot product with that. Okay. So you see now again, this is also in that form. Where is it now? In that form. It's just that the coefficient looks slightly different. We're after the coefficients because I've already said all of them will look like this, right? So the coefficient for piezoelectric LA longitudinal acoustic piezoelectric scattering mechanism is electron charge times piezo coefficient over dielectric constant, low frequency dielectric constant. Okay, so makes sense. I mean, and then you can check here whether the units are right or not, and you'll see actually it's correct. It's in the energy over distance, because you see piezo is charge over area, coefficient is charge over area, and q square over c is energy, and you can check that. So, yeah. Okay, so the last one, which will be the polar optical phonon, is kind of the interesting one. This is also called Froelich interaction, after Herbert Froelich, who really kind of contributed heavily to understanding it, and he almost went ahead and he tried to explain superconductivity using this, but I think the last step was taken obviously by the Bodine and Cooper and Schreifer, but it is really based on the Froelich interaction. So this is the last one, and we're going to look at this now. So any questions? I mean, this is a general formalism, how you try to pull out what is my W, and once you know your W, I'm just tabulating this whole thing right here. Yeah. There, yes. I mean, pretty much that's the argument. That's the argument, and you can. That's right. But you can see it's an approximation. Since the free charge density is way lower than everything else, and if you don't want to make that approximation, actually what happens is this thing becomes frequency dependent. That's all. I mean, it was the Lindauer thing. It just becomes frequency dependent, and so that any presence of free charge that can contribute to screening and such is absorbed here, and you still maintain a 0 D. Okay, so let's look at this. Any more questions? Yeah, Sam.
So why doesn't that appear inside of the deformation potential? It seems like it's just pulling atoms apart and changing the electrons.
Why doesn't the which one? Oh yeah, good question. You're saying why is this so decoupled from that, right? No, I mean it doesn't have to. You can add, meaning that's right. So your total thing will be this plus this now. Is that what you're saying? Yeah. And in the end we're going to basically add all of them anyway.
Why is that term not already inside of the
Yeah, because it says that there are some materials where they are not piezoelectric. So you're saying that when you sum the two, the total, if you have both polar material and if you have a polar material, then both of them are present. And why is it that we didn't already include it here, right?
Well, how did we define UC? We said it's a matter of like pulling the atoms apart and changes.
Yes, that's right. That's a direct effect of strain, and the Coulomb energy was not taken into account there. You can, you can clearly say that, well, I'm also going to take Coulomb energy. I'm going to redefine my DC, which absorbs this. That's fine. You can do that as well. We're just thinking of it separately right now. But you can do that. And when that process goes to an extreme, then you have polarons. Then you basically, it's so polar that electrons trap themselves. And this is when it's very weak. You can consider them separately. And let me say that when we talk about the superconductivity aspect, we will talk about this polaron when it becomes coupled very strongly. What happens? Right now, for most semiconductors, you can do the numbers. The piezoelectric scattering. I think we had a little plot some time ago, and you can look at their relative strengths by looking at, where do they figure in this whole picture. So, okay, so here's piezoelectric scattering, and here's the deformation potential acoustic phonon scattering. So around room temperature, the deformation potential wins out typically. But at low temperatures, the piezoelectric is very heavy. I mean, actually, it's the dominant one at low temperatures if you don't have impurities. And the reason for that is really the Coulomb interaction stays independent of temperature. I mean, it doesn't care about temperature, right? So it stays independent. And if you do the numbers, I mean, that's where it ends up being. So this is for typical semiconductors. Now you go to some other, crazier materials, then this can completely dominate and things like that. So right now we are treating them as independent channels of scattering. And I think your question is why are we not treating them together? And that's when we plot them together, we'll have very strong coupling of electrons and phonons, and those are your quasi-particles like polarons and things like that. So similarly, okay. So that's you can see essentially these are just additional coefficients that proliferate as you include more and more scattering mechanisms. So let's now look at the polar optical phonon scattering, and this part is the strongest scattering mechanism in a polar semiconductor at room temperature. It dominates over piezo and acoustics and all that stuff. This basically kicks in and it's the strongest. For all 3-5 semiconductors that we typically use in electronic, ultra-fast devices, lasers and all that, this is the dominant scattering mechanism, the polar optical phonon. And the mechanism is really the same as we have discussed till now. You have a longitudinal optical mode, and just like you already asked, I mean, we did the thing for deformation potential. Now we want to do the Coulomb part of it now. If you so what we want to find is W of R of t for polar optical. It's an optical phonon, so you don't need the divergence of the strain anymore, right? So you see you're getting a charge scattering directly from the amplitude of vibration, not from, you don't need strain anymore for this. I mean, rather you don't need, so it's an optical mode, so your scattering potential will be directly proportional to, okay, it will be directly proportional to that because that already is creating the strain because they're out of phase, right? The charges are out of phase, so it's already creating the compression and the dilations here, right? So does that make sense? Okay. But it is Coulomb, so it's kind of doing what we are going to do exactly what we did here, except now we are going to do not for the divergence of u. We won't have divergence. You have directly from the amplitude now. Okay, so same thing. But so here again, we look at it as dipoles that are. Actually, we go through pretty much the similar procedure, but here we're going to just write it in a slightly different way. Okay, so this mechanism is present. So again, we write the displacement as at low frequencies as this plus a polarization, let's say at low frequencies. When I write 0, it means low frequencies compared to light frequencies. Optical frequencies very low. Even gigahertz and all are still low frequency. We're talking, when I mention high frequencies, that would be a terahertz, for example. Let's write it as very high frequency, optical frequencies. And let me explain if it's not clear what I mean here. Okay. So now I'm writing two situations. We're dealing with optical phonons. So here I didn't quite write it as a function of frequency, but here I'm writing it as a function of frequency because the polarization of the crystal when you reach extremely high frequencies cannot quite keep up. When the electromagnetic wave, that is, what is this frequency? So we have the lattice, positive, negative, positive, negative ions, going through, and then we have what we are doing here is we put an electric field, but that I am oscillating with a certain frequency. It's kind of going back and forth, very large, 0, negative, large, very high frequency. Right? So as the electric field goes back and forth really fast, now you can see that the electron clouds and everything has to respond. Right? It is Coulomb charge. So all of them have charges, so they have to respond. And at very high frequencies, for example, the electron clouds can respond to a certain level, and then there's at extremely low frequencies, even the ions can respond; they can move, right, at very low frequencies. Meaning, even though they are heavier than the electron clouds, they can still move and screen out the field. So right from here, you can see that as you increase the frequency, less and less charges can respond. Therefore, your effective dielectric constant with as a function of frequency must drop. You know that, right? The effective dielectric constant, which says how much is the electric field screened inside the material, should drop. So, and it drops. So the value at high frequencies is what you would call epsilon s infinity. Values at low frequencies is what you would call 0, right? And they are actually related. The dielectric constants at 0 and at high frequency are related to the TO and LO modes. Let me make sure I write this correctly. Okay, so so it's there in one of your slides. Let me pick that up. One would typically do it in a solid state physics sort of course. So epsilon 0 over over TO. So TO whole squared. Okay, so if you know your LO and the TO mode energies at the edges of Williams zone, so this is called a Leiden-Sachs-Teller equation. Again, I mean, these are well known for most materials as well. So the two things, high frequency epsilon and the low frequency epsilon, are related. The high frequency epsilon is is lower than the other one, and they're related in a certain way. And that means, all that it means is your net polarization is weaker at high frequencies. So it cannot really respond very fast. And using this, I'm actually going to kind of so the polarization in a unit cell is given by how do we define macroscopic polarization, just like we were doing there. Here you can define it as the dipole moment, how many dipoles you have per unit volume. Okay? So, and let me explain exactly what I mean by these quantities. The polarization has units of charge per coulombs per unit area, centimeter square, just to be consistent with everything else here. Remember, displacement and epsilon at E, these all have units of coulomb per centimeter square, and so should the polarization. And microscopically, at least the classical theory of polarization is if I have a little volume and I have a lot of dipoles inside it here, a lot of dipoles that are like that, electric dipoles, then you essentially sum, let's say each one of them is pi, right, is the dipole. You sum them all over that volume, and you get a net dipole moment. These are all vectors. You sum them, and you get a net dipole moment. And then you divide it by volume. That's what we mean by the polarization of a material. So clearly, if they're randomly oriented, there's no polarization. If they're all oriented in the same direction, you have a large polarization, and so on. And what is the dipole moment? Well, for a crystal like this, the dipole moment, if you let's say this is a unit cell for you, omega, and the dipole moment is written as electron charge times. So there is a certain effective charge times the distance. Okay, so the distance q star. So let me make sure I use the right units here. Okay, q star for E star. E star is the effective charge on these two times the distance. And what's the distance? Well, that's basically how much have they changed, because of the vibrations, divided by this. Okay? So that's really the distance, which essentially this is u1 minus u2. For example, if this is u1, the displacement of this is 1, this is 2, so u1 minus u2 is delta u, divided by the volume of the unit cell. So that is what this quantity would be. That's the polarization of the material. What are we doing here really? It is as simple as what is the definition of a dipole? Well, you have negative, positive charge. If your charges are, if the charge is E star and the distance between them is d, then the dipole moment is E star times d. That's the dipole moment, right? That's really what it is. Dipole moment divided by the volume is the quantity here. And so you get E star over volume. Okay, so that's really what enters this picture, and this E star is the key physical parameter. The only new thing here, everything else we were going to do is exactly the same as this. But E star is the new one. It's called the effective Born effective charge, and it's a measure of how polar is the crystal. How polar is the crystal? Meaning, if I have silicon and silicon, E star is 0. There's no polarization in this. If I have gallium and arsenic, E star is something. If you have gallium and nitrogen, it's 10 times more. If you have some other polar crystals, highly spontaneous, for example, close to ferroelectrics, this will be even 10 times more. As an example, in a ferroelectric, E star is effective charge. The distance between them is of the order of angstrom. I mean, it's not, but the charge here for a ferroelectric would be of the order of atomic, 1 electron charge. 10 to 1.6 minus 19. For weak, for gallium nitride, which is extremely polar, almost an ionic crystal, that is roughly 1 out of 100, or 5 out of 100, E star. Gallium arsenide, like 0.1, rather 1 out of 1,000 or less than that. Does that make sense? That's the charge. So order of magnitude. So how polar are things? Okay, so once we have this, and how is E star, this Born effective charge, related to other quantities? And this is a very important quantity. So E star by epsilon squared over unit volume whole squared. This has a very nice relation to I think I did, yeah, okay. So this is equal to, I'm just writing this down, I'm not deriving it, but you can look over maybe Kittel or Ashcroft. I mean, this is derived in most books, okay. So it will be the mass density times the phonon frequency, the optical phonon. Remember, we're talking about optical phonons here. So the optical phonon has a frequency omega naught squared times the epsilon. So actually, let me make sure that I don't write it wrong. So yeah, epsilon naught times omega naught squared. Okay. Okay, and then there's a difference of the low and the high frequency dielectric constants. Actually, sorry, and I will give you the handout here. Oh, by the way, yeah, it's done nicely in the handouts I already posted. So that's how it depends. Meaning, if you want to find out what is E star, you have an expression for it. Everything is known: material parameters, optical phonon frequency. Rho happens to be the mass density, kilograms per centimeter cube of the matter in the crystal. And that's where all this mass of the atoms and all that comes in. I mean, it's a phonon, so it comes in here. Epsilon 0 is the permittivity of vacuum. High frequency dielectric constant, low frequency dielectric constant. And it's actually a difference of the two, so that causes this vibration. And okay, so you can plug in the values. These are kind of well known. Typical numbers of epsilon 0 would be roughly 10 times epsilon naught, and this would be 5 or 4, depends on the material. Yeah? So 1 over 5 minus 1 over 10, that sort of numbers. Yeah. Okay, so once you have that, the value of this E star, you can go back and write it down again, and we want to bring it into this form. Okay, and that part is, again, we kind of go the same route and say that we have a displacement, and displacement is epsilon naught plus p, and take into account that the displacement field is of a zero divergence, and then again integrate the electric field. I'm not writing that out, but from exactly the same procedure as we did here. We remember we have an extra term here, which is, I think I erased it, but that E star term. the extra term, and then you go forward and you basically have found the electric field. Well, let me write that down. Why not do that? So the electric field r comma t is equal to this E star that we saw. This the Born effective charge over volume times epsilon times electric. And then there's a epsilon infinity. So when we write this del, actually it pretty much is your U. So the vibration between atoms, and then you use this to integrate and find is E star, and there'll be a I. Remember, when you differentiate, this is U of QS e to the power I omega t. When you differentiate, this IQ came to the numerator, but when you integrate, it will go to the denominator. The amplitude of that will go to the denominator. So this W of RT would be this over I QS. I'm looking at the magnitudes here, absolute values, and epsilon infinity times I QS dot R minus omega t. Okay. So yeah, we integrate this, and this thing comes over here, and therefore again this thing is our coefficient which we were after, and it looks like E star, and there's a QS in the denominator now. Okay. There's a volume of unit cell and things like that in there. Okay, so. Oh, sorry, I forgot the electron charge. See, I was wondering what went wrong. Q is the electron charge, and there'll be a Q. Okay, yeah. So we have collected all four terms, and now the question is, can we move forward and find the scattering rates? And I'm actually not really going to go through the whole process, but I will outline just for one how to calculate the scattering rate and how will it lead to these temperature dependencies that we had discussed earlier. And the second thing I'll do is I'll point out the effect of Froelich interaction here and how can it lead to these correlated effects. Okay, sorry, I think I've spent quite a bit of time on trying to get this all these forms, so that's all right though. Okay, so what we'll do is just look at the net scattering rate now. So we have all the matrix elements, they're all in this form, collected them, and again go through these by yourself once, and I think it will be clear so what all these quantities are. Just to mention that QS, the wave vector here, there's a QS here and these two, the deformation potential optical phonon and the piezoelectric acoustic phonons, they don't depend on the wave vector. They don't depend on the wave vector. So these will typically be, essentially isotropic sort of scattering events. But let me explain now what we're going to do. So we want to find S of electron states going from scattering from K to K prime, and for that, we want to find this whole matrix element squared W K prime squared, and then it will also all right. So it will conserve energy because of absorption or emission processes. Okay, so that. And essentially the steps would be first evaluate this, right? And then take a square, and what we have is this quantity here, and then it's multiplied by the whole phonon vibration amplitude and the wave. Okay, so that term essentially will look like if I have electrons. Let's write this down: R, comma T, and K prime. That's what we have to evaluate now for each one of these, and you can see that that there are these quantities multiplied by all the others. So let's write it in a more generic form. We write it as an integral of over space, right? If I'm dealing with three-dimensional electron systems, then I do three-dimensional space, two-dimensional, whatever dimensions you are in, use that one. Okay? And if your scattering is within the same band, if the electrons are scattering from conduction band states into conduction band states, I'm also going to call upon that fact that, well, my whole wave function is envelope function times the block function, a periodic function. But the periodic function integrates out to 0, so I can pretty much think about it from a... Now this argument that I'm going to write my k state as e to the power I k dot r over square root of the whole volume, crystal volume, and e to the power minus I k dot r over square root of crystal volume k prime. Okay. So that's k prime. This only holds if your scattering is within the same band. So one of the processes that I don't know whether I have time today, maybe not, to discuss, but I do intend to discuss this later on, because even though it's so one of the processes, for example, if I have a very high electric fields in a semiconductor, and you have electrons coming down here. So this is not quite even right. I mean, if you have even higher fields, then the electrons can actually interact very strongly with in the conduction band, can interact very strongly with electrons in the valence band, and they can impart instead of so essentially they can kick this electron out of the valence band, and it forms a hole, and you form 2 electrons here, and then 2 electrons go in, and the hole goes up, and the hole can so basically this is called impact ionization. Okay? Ionization. And actually, similar procedures that we have used can be used to calculate this, except here you are going from the conduction band to the valence band. So here I can't make this sort of approximation. You have to retain, if you have any interband process, you must also retain the periodic paths here. Okay? But if it's intraband, you can, because the intraband part of the periodic functions is the same, so it kind of integrates out to 1, so you don't need to bother about that. The other part, for these higher energy phenomena, we will look at it later. Okay, so and I do intend to look at it after we cover things like Dirac equation and such. So then it becomes a little more natural to cover that process. But today we are just going to look at this low energy part of it. So the potential is of this form. I mean, that's did all the hard work for its potential is of this form, and what I'm going to do is write. I'm going to just write the omega of qs, which we just kind of this part which we wrote down for all of them. Yeah. So you just pick them up, whichever scattering mechanism you're looking at, times e to the power I qs dot r, and I'm not going to write omega t. I'm not going to write this term. And why? Because why am I not writing the time dependent part? Because I already have done that. Where is it? It's already given me this. Right? So it's done. Time part is already done. It's there, and the space part is here now. So this is space integral. Okay. So now you see what you have here is a Fourier transform still, but slightly different. So now you have your k's look like this. Okay. You see, this is how your k's will look. There's a wave vector difference e to the power I. So k, the initial wave vector of, or you can think, I mean, k is a proxy for momentum. H bar k is the momentum of the electron. So right, it's initial momentum minus final momentum, right? And then there is okay. So remember, this part is typically this plus its complex conjugate, meaning a potential that an electron sees is always real, right? So you have a wave going, this is a wave going to the right, and then you'll have a wave going to the left. Does that make sense? I mean, the potential that an electron sees is always real. So you'll have e to the power IQRS, and you'll have e to the minus IQRS from the second term. Okay? And one of them will lead to absorption process, the other will lead to emission process, so plus omega q and minus omega q. So that plus minus is already there. And so I should actually, what I'm saying is I have another term like this here, another term, right, which is the sum. And so I'm going to just again merge them as plus minus this QS dot R, right? You see that, right? So you'll get that. And then you get the W of Q, but you see that W of Q is actually independent, so that just goes out, right? None of these have R in it, right? Let's pull that out, right? Pull that out. And what you are left here over volume, what is this quantity? It's an integral of all space of e to the power this quantity. Right? So what is this? All space. Maybe you can, yeah. What do you get here, right? It's a what? Yeah, it's a delta function, and here you see it's actually dimensionless. You look at it, right? Volume over volume. It's dimensionless. So this is actually a Kronecker delta symbol. Kronecker delta, not a Dirac delta. Makes sense? And how do you want to look at it? It's basically you have this factor here. You can think of it as this dot this is a theta, right? And you're integrating an oscillating function over a very large volume, right? And if you have an oscillating function and you integrate over a large volume, you'll always get a zero, equal number, equal and opposite positive and negative phase, except for the situation when that phase is constant, right? And when is the phase constant? When this thing is zero, right? Does that make sense? Sorry, except when that phase is 1, right? So I mean, e to the power theta is 1. So essentially, that's why what you get here is W of QS times a Kronecker delta of K minus K prime. All that it ensures is this thing is equal to this thing, minus plus. Okay. Does that make sense? Okay. So is equal to plus minus QS. Okay. So or K prime is equal to, K is equal to K prime plus minus of QS. Is that clear? And then you combine the two, and you write this thing here as scattering rate from K to K prime is equal to this matrix element W of QS whole squared. And this you just look up from here. You have a table. You just look it up. Right? And then you have a Kronecker delta squared. What is the square of a Kronecker delta? It's itself. Right? If this is equal to this, you have a 1. If this is not equal to this, you have a 0. You square that function, you get yourself again. It's the same thing, right? So you again have a Kronecker delta here, K minus K prime, comma, plus minus QS. Okay. So that's your full-blown scattering rate for electron-phonon interactions. And what it's really is kind of very telling that you have a scattering coupling element depending upon the exact mechanism. And every process of phonon scattering, be it acoustic, optical, whatever be it, is going to conserve energy, and it's also going to conserve momentum. This is a momentum conservation. Okay, initial momentum, the difference of the electron momenta is picked up by the phonon momenta change. So that's the energy and momentum conservation. And this looks like two separate relations, and later on, okay, so we're going to actually see that, let me not discuss that now, but once you realize this, and then you also know that depending upon the phonon and electron energies, so if your electron energies are h square, k square by 2 times some effective mass, E of k prime is h square k prime square by 2 times effective mass, right? If they are in parabolic bands. It doesn't have to be. You can take some other materials, graphene or something else, but I'm just doing it for parabolic material, parabolic band structure. And h bar omega qs is equal to, we're going to make some approximations. Let's say acoustic phonons, we are looking at very low energy phonons at near, in this part of the dispersion. If you're looking at very low energy phonons, then for acoustic modes, then this will become h bar times the sound velocity times qs, right? Remember, that's what we have talked about. Because frequency is sound velocity times the wave vector for acoustic phonons. Right? And for optical phonons, this is essentially h bar times optical phonon, whatever beats. It's constant. We're going to assume that that thing is a constant here, h bar omega optical. we're simplifying it. You don't have to. You can do a full band thing, meaning you take your cosine k or the full dispersion, but we're just simplifying it right now. And it works really well for most semiconductors this way. So h bar omega, we found an expression for this. We found expressions for that, for that. These are all scalars inside the Dirac delta function that conserve energy. But in the Kronecker delta, these are vectors. These are vectors because they conserve momentum. Momentum has direction. Right? What is the direction conservation? Well, if this is h bar k, and okay. So essentially, the momentum conservation is really saying that if I have an incident momentum, an electron that's incident, and then let's say it absorbs a phonon with some phonon wave vector, and then it's going out at certain different wave vector, right? Then clearly the total momentum is conserved. The energy conservation is taken care of here, from here. For absorption process, you will get that Ek is equal to, so Ek prime is equal to Ek plus h bar omega qs. That's absorption, right? Phonon absorption. So inside, and emission would be minus. So let's do it this way. Absorption is on top, emission is on the bottom. The signs mean what they mean. Similarly, for momentum conservation, you get h bar k prime is equal to h bar k plus or minus h bar qs. Right. Again, absorption and emission. So you see, actually, what I'm trying to indicate here is that these two relations are coupled to each other because K's and Q's are shared between the two. If you're doing acoustic modes, you take that. If optical modes, you do that. But you can actually take this now, and from here, you can take a dot product of both left and right hand sides with itself. Okay, so you get K squared, K prime squared is equal to K squared plus or qs squared plus or minus 2k qs times cosine of theta, where theta is the angle at which angle between k and qs. So, right, and you can use this. You substitute it back here, substitute it all back here. Okay? And I'm not doing that, but what happens is the Kronecker delta gets absorbed into the Dirac delta. I mean, you get one expression because the k's and q's are really related to each other. And the expression you get is kind of written out here in detail, and maybe that's a good point to end the class today. Let me write that down. Yeah. So this part needs a little bit of algebra, but it's really not complicated algebra. It's so okay. So this the rate. What I'm trying to really do now is this part, because you have these two relations. You can use these to collapse this into one, right? Into one, and when you do that, this expression becomes k to k prime is again 2 pi over h bar. This w of qs whole squared. All these are the w of qs's, and this whole term now. Now, kind of interesting. So remember, all of them have u of qs. This term, right? And when you square it, see, I missed this. I think yeah, that's right. It's not here. You see, so there is a u of qs whole squared. I missed that term. I didn't write it here. It should be there. And this we derived in the last class. Towards the very end. I mean, we spent maybe just a short minute or so to derive it. But what is that amplitude square? From a correspondence of classical oscillator with a quantum mechanical oscillator, we wrote down that the amplitude square is Planck's constant, or twice frequency of that phonon mode, mass density volume. This is volume of unit cell times the phonon number, Bose-Einstein distribution. So that sits in the front. So u naught square. We have an expression, is what I'm saying. And this part is actually, if you have phonon absorption, it is number of phonon absorption process is proportional to number of phonons. If you remember way back, we discussed about spontaneous emission and absorption processes. Absorption processes are proportional to number of phonons that are already there, but emission process will be 1 plus this, proportional to this. And then this part, we are kind of ad hoc building it in here, but once we look at this second quantization, this will come out naturally, so I'm not, okay, so rho omega naught times n of phonons plus, so you see for absorption processes it's NQ, and emission it's NQ plus 1. So we write it in this kind of a crazy way, so plus half plus minus half. So for absorption processes you choose, maybe we write it minus plus, okay? So absorption, emission, make sense? Absorption they'll just cancel out, you give you NQ, emission you'll get NQ plus 1, that's all there is, okay? And then there is this whole big factor which conserves energy, momentum, and all that, which, okay, so. So I wrote that, and then this the whole Dirac delta. And the Dirac delta has a cosine theta. Let me write it, and then we'll stop there, okay? So there's a cosine theta. And these things come about from these two relations, really. I mean, you just go through this algebra, write it down, take this, and take this, and essentially substitute this here, inside here, and the energy term. Sorry. So take this and substitute it here, and you'll get that whole thing. And it has a Dirac delta of a cosine theta, which is the angle. Qs is the phonon wave vector over 2k. K is the electron k, electron momentum. Phonon momentum and electron momentum, Qs by 2k. And phonon energy by, omega q is the frequency of the phonon divided by VQs. So let me write that. The phonon wave vector over 2 times the electron wave vector. And then you have a phonon frequency over velocity of electrons times the phonon sound wave vector. So velocity times wave vector is a frequency. Okay? So you have this whole thing, and there are some signs which are depending upon emission or absorption. So the minus would be for absorption, plus would be for, so all the signs upstairs here are for absorption. So plus minus, all these will come out if you do it right. I mean, this thing, just keep track of it. Okay? So, I forget, so it's plus minus. You can always look it up. Oh, the other way. Okay. Yeah. So, and then you have the scattering rate now for one k state. You just have to kind of sum it over all final states, k prime, and you end up with all these formulas now. So that's that part I'm not doing. So you end up with all these formulas once you sum it over all final k prime states. Get this. So for acoustic phonons, for example, you get, you started with deformation potential, you will get 3/2. Mobility will go as -3/2 and things like that. Deformation potential is sitting here. The piezoelectric will give you this, okay, and so on. So I'm hopefully, it's clear how to go about it. But and polar optical phonon will look like that. You have that little, Born effective charge factor here and all that. So that appears there. And for polar optical phonon, the n omega, the number of phonons the number of phonons is always Bose-Einstein. And let me just finish by saying this part here, that the number of phonons, which is, you see the phonon scattering rate has become proportional to number of phonons here. Right? Phonon scattering rate is proportional to number of phonons, just like impurity scattering rate became proportional to the number of impurities, the density of impurities. Similarly, the phonon scattering rate is proportional to the number of phonons. Where did this come from? It came from the amplitude squared, and then we made the correspondence between amplitude squared and the number of phonons. And what it means is, if I'm looking at acoustic phonons and you are looking at very small q vectors, then the number of phonons is equal to 1 over e to the power h bar omega qs over kt minus 1, right? But with acoustic phonons, we are looking at very small energies, very small. All right. So you can take e to the power a small number compared to kt. H bar omega is small compared to kt. E to the power small number is close to 1. So you do a little Taylor series here. and you expand it out, and what you get is essentially kT over h bar omega qs, right? If you do a little Taylor series. And it's very interesting because the number of phonons then is the temperature, the energy of kT divided by the phonon, each phonon quanta. Right? That's the number of phonons for acoustic phonons. And acoustic phonons are very small energy, so therefore actually it's almost quasi-elastic scattering almost. Whereas the optical phonon, you can't do that. You have to, I mean, here optical phonon energies are about, typically larger than room temperature kT in most semiconductors, so you can't do that in optical phonon. And that's why for acoustic modes you get basically a power law of temperature dependence, whereas for optical you get the full exponential Bose-Einstein dependence, which I was trying to mention. So acoustic phonons will look, some power laws, but this is really the exponential Bose-Einstein. You can't really make that approximate. Okay, so I think again a bit over time again, but let's. So I'm going to. What I want to do is next class I want to get started on the next topic, and I will probably not probably. I want to do the one class which shows diffusive localization processes from a path integral approach. So we'll develop a little bit of the path integral approach. And then we'll talk a little bit about spin and move into all these geometrical and topological aspects. Okay, so I'm going to end the part of Boltzmann transport here, and a little bit later, after we cover a few topics, I want to come back to the impact ionization process because that's very nicely covered by these modern techniques today, rather than the older ones. Okay, good. Thank you.